Okay, before we get started on our trigonometry study, I'm sure I don't want to spend too much time on, but issues concerning your your graphing assignment. Those are not easy problems, but hopefully some of the tools we've come up with recently now allow you to do some of that. Yes. 33? That's on 4.2, right? Okay, we're going to take a look at number 33 on 4.2. At least, yeah, we'll see how far we can get into this. So, okay, basically it's a problem of, see if you can graph this thing. Two x squared minus 5x minus 3 and that's all over x cubed minus 2x squared minus x plus 2. And the directions are identify all the intercepts, find any vertical and horizontal asymptotes, check for symmetry, plot additional solution points as needed, and try to sketch the graph of this thing. Okay. Well, let's do what? Let's see if we can at least approach the asymptote question. If we're going to have a vertical asymptote, it would be because something in the denominator could be 0, right? Well, we can't tell by looking at this. At least I can't. Although, that one doesn't look like it's that terrible to factor. Did anybody try factoring that by grouping? Or let me put it the old divide and conquer technique. What I mean by that is if you take out of the first part, you could take an x squared. Then that would be x squared times the quantity x minus 2. And out of the second part, you could take a negative 1. And so even though that's not factored, do you see now that there's a common binomial factor? And so now, I don't know how many of you can see this. The denominator has the factor x minus 2. It has the factor x squared minus 1, which means, whoops, it means what? X squared minus 1 is the difference of two squares. So we have the factors x plus 1 and x minus 1. And so now I know where the vertical asymptotes are, don't I? They're located at 2, negative 1, and positive 1. Okay, that turned out to be surprisingly nice and easy. Let me ask you this. Is there a horizontal asymptote here? Actually, we don't even need factoring to do that question, do we? Christina? And the reason is that, yeah, the degree of the numerator is 1 less than the degree of the denominator. So I don't know, we pull out a grid here. Let me grab a graphing grid. So we know that we have a, let's see, we have vertical asymptote. Okay, we have a, let me grab a, okay, we have a vertical asymptote at x equals 2. This is a little bit crude, but it should work. We have one at negative 1. And we have one at positive 1. Wow. You know what? I maybe should have each thing stand for 2 on here. Let me try this again. It's going to be awfully crammed together. So I'm going to just move this. This is going to be my 1 at 2. This is going to be my 1 at -1. And then my 1 at +1. Is okay, so try to remember my axes. You know, each of these is worth, this is 1, 2, etc. Okay, -1. So each line stands for 2 units. Otherwise, it looked like it was going to be too crammed together. And thanks to Christina, we also know there's a horizontal asymptote at x = 0. Okay, well that helps a lot already. We'd like to know the zeros, though, wouldn't we? And the zeros are what? The points where the graph actually crosses the x-axis. And which part of our rational function will give us clues to that? I'll give you a hint. It's either A, the numerator, B, the denominator, C, some other source. It's going to be the numerator. Because here's why. If the denominator is 0, do we get answers? No, we get garbage then. But so when can 0 come out as an answer? Only when the top is 0. Okay, so when is the top 0? Well, the only way I can really find out is if I factor the top. So we would like to factor that. Okay, so let's try it. And I'm going to just be real optimistic and try to factor it right on the spot here. May not be able to. We, for 2x squared, probably have a 2x and an x. Then we need a 3. And that's going to be what? A 3 and a 1? Let's see. Inside term plus 1x. Inside product 1x. Outside product next. We got it. Cool. Now, when will those numerator factors be equal to 0? When x = 3. So we have a 0 at 3. And when 2x plus 1 = 0, can you do that in your head? 2x plus 1 = 0. 2x = -1. X = -1/2. At x = -1/2, I shouldn't have made those so fat, but I wanted to emphasize that we now know those points. Okay? So, does it shock you real much that we're actually crossing an asymptote here? You hopefully learned last time that can happen, right? Okay. So now what? It's time to start investigating, huh? Should we pick some points near the asymptotes, see what we can find out, make our sketch, and then off we go? So I don't know, did anybody, can save me a little time here, did anybody pick some points like just slightly larger than 2? Nobody? Okay. Well, I don't know if I want to spend more time on this, but let's just say this. What you would do now is, like, I would pick, I don't know, 2 1/2 or 2 1/4 or something, and I would plug it into my function. I'd get the answer, and I'd find out if we're up here or down here. It's got to be one of the two. And wherever you wind up, remember, you're not going to get both, because then it wouldn't be a function. That's not going to work. So then you know what the asymptote, you know, if the point does turn up here, then we might, who knows? We don't quite know what's going to, it might, we do have a crosser here. So maybe this comes down, crosses, and comes back to the asymptote. Sometimes that'll happen, where it'll cross and come, and then start. But now you almost have to plug some points in and see what happens. We could investigate symmetry and all of that. These problems are pretty long. I would say those are the beginning points. Does that help you? Okay, I think we'll leave that one at that then. Other questions? The only problem with these problems is if we were to do one to completion, about half the class period at least. And the problem with that is then you don't have any time for new material. But so there are some difficulties with these longer assignments. All right, this is a big red letter day. We leave. I shouldn't say we leave algebra because there's going to be a little bit of algebra involved, but we now embark on a brief study of trigonometry. I gave you guys an outline. Yes. You must have come in afterwards. There you go. Anybody else? I got one. I don't know. I've taught this for years, and I just kind of developed. I developed what I think is the best way. I wouldn't show it to you this way otherwise. In fact, it's a little bit harder because I have to coordinate my outline with whatever book I'm in. And honestly, it'd be easier to use the book, but in that way. But I really think this is better. What we'll be doing, this may not seem like much, but I've outlined 8 or 9 classes that we're going to spend on trigonometry. I actually planned for 9, and kind of divide this up into 9 parts. I've got it divided on the MyWLC site. If you go up there, you know, I call them Trig 1, Trig 2, Trig 3, and so forth. At least on my WLC site, I think I went up to Trig 8. Oh, I should show you that. So it might be a hair hard for you to find. So let me show you this. When you go on to the my WLC site, and go into the pre-calculus, it's almost hidden. Here it is, way down here, trigonometry. You see that? In fact, I hadn't looked at this since I created that a year ago. And I couldn't remember where it was, and I had to look for a few minutes and go, where is it? And I was looking up here, and where is trig? Oh, it's down below. Again, I'm not quite sure why Genzibar does this, but I cannot edit any order of these buttons over here. I've asked the experts. There's no way to do it. And they just kind of show up where they show up. It's really weird. Okay? Otherwise, I would have had this up by the rest of our material. But anyway, if you click on trigonometry, then you'll see the outline appears, and I've got it, you know, like at the end of lesson 1, you'll see a note, Trig 1, notes from class. And then here's the second part, notes, Trig 2 notes from class. So they don't, you know, it's not like I'm going to do Roman numeral 1 on day 1, Roman numeral 2. I take a little bigger chunks than that, but it'll be pretty obvious. Let me remind you, and I think I go down to Trig 8. There might even be a Trig 9. Okay, I want to remind you that to get this, to get trigonometry, this is why it bothers me, and not everybody's here, because we really have to get in this together. We have to get all these details, and we have to get them up here. And so I'm going to be asking, they're not a lot, but you've got to memorize. You've got to really know some of this stuff. So when I ask you what the sine of pi over 6 is, you're going to know that it's 1/2. It's just going to come out. That's my goal. Okay? And I know it can be done, and we've done it before. In order to aid you in this memorization, you may question my use of the word aid here, but in order to aid you in this memorization, I am going to give you many, many, many quizzes. Okay, so quizzes are going to come flying at you quite frequently, practically every day. If you're on top of it, you're going to nail it. It's not going to be very hard. If you're not good at memory work, this could be a real problem. You need to maybe get together with some, I don't know, figure out a good way to do it. Okay. So anyway, stay with us, and I think your trigonometry is fun, and it's really, if you memorize the things that I'm going to show you, you'll be able to do just a ton of trigonometry on your feet. And that's exactly what we need you to do when you go to calculus. Either kind. Either the Calc 1 or the Math 210, the survey of calculus. Okay. There are 6 trigonometric functions, and we've been studying functions. So this is just an extension, but these guys aren't algebraic. It's a different kind of creature. Very predictable and beautiful patterns, but just a little bit different. Okay, so to make our beginning here, you probably figured that, know that already, but trigonometry means triangle measurement. And so this is all, a lot of this all comes from the geometry study of triangles. And so you'll notice my outline begins. It says, hey, this thing has its roots in geometry. There's a few really important basic principles from geometry that lay the whole foundation for this study. One of them is similar triangles. But before we do similar triangles, I want to talk just real briefly about congruent triangles. You can remember, I'm sure you remember, how many days did you spend in geometry class proving triangles were congruent? Probably quite a few. And you learned things like SAS, SSS, ASA, hypotenuse and one leg. Anyway, maybe you remember that. And then you probably used corresponding parts of congruent triangles are congruent 3,000 times. What do you need for two triangles to be congruent? I don't mean SAS or ASA, but if two triangles are congruent, what does that tell you about the two triangles? Just a quick review. If two triangles are congruent, then what do you know about those two triangles? The corresponding angles are exactly the same size. Yes. And? What's also true? The angles are equal. Aren't the sides equal too? The corresponding sides have the same length. And so the way I taught it to my class was congruent means what? Same size and same shape? They were basically copies of each other. And everything matched up. So if you knew one triangle, you knew the other one. Okay, now what's different about similar triangles, which is in part B of the outline? Well, yeah, I guess I shouldn't have pointed you to the outline because I really didn't want you to read off of that. But similar triangles are also the same shape, aren't they? But what's different? Okay. Let's try that one more time when he was talking. That's right. Or just in general, the size of the two triangles is different. Absolutely correct. But even though the sizes are different, you do know something about the lengths, don't you? In similar triangles, the corresponding sides are not equal, but they are proportional. Do you remember that? So in that, look at your outline and look underneath the two similar triangles in part B. You see how all the matching angles are the same? Angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. And right below it, what do we have? A proportion with 3 parts in it. AB, that is kind of the left side of the big triangle, is to DE, the so to speak left side of the little triangle. As AC, the right side of the big, is to DF, the right side of the little. As BC, the bottom of the big, is to EF, the bottom of the little. So it's just, it's almost like these old, what? I know you've taken these crazy IQ tests where they draw pictures and they say big giraffe is to little giraffe as big monkey is to, and then they give you a multiple choice, and you're sure not going to say little rat, right? You got to keep it. You got to keep the analogy to be consistent. So, okay. Similar triangles is what makes trigonometry possible. Those equal ratios that you see at the bottom of the screen there, that AB is to DE, as AC is to DF, as BC is to EF. In fact, we could even throw another one in there. We could say as the perimeter of the big triangle is to the perimeter of the little triangle. Anything lengthwise is going to be in that same ratio. That's what makes trigonometry possible. Okay, so here's your first candidate for a quiz question. What makes trigonometry possible? Similar triangles and the proportions that result. Yes. Okay, that's, I think, very important to recognize. Back to our diagram here. So, okay, now, a little tiny bit of, I don't know what this is. I guess it would be somewhere in the field of algebra. But we're going to do a little bit of work that, reviews some things from the past. If we knew this, let's just say, so that we can begin, we have this proportion. All a proportion is what? 2 equal fractions. Here we have a proportion. If you know that, did you know that this will also be true? Now, really, what I did is I took the top proportion and I kind of read it sideways. A is to C as B is to D. Now, let me prove it to you. Let's put some numbers in here. How about if we do 4 is to 8 as 1 is to 2? Okay, does that appear to be correct? Okay, now write it sideways like I just did. 4 is to 1 as 8 is to 2. See how it works? And by the way, how do you check if a proportion is correct? How do you prove to me that 4 over 8 is equal to 1/2? Well, there's a couple of things you could do. I know you're probably thinking he's lost it because all you have to do is simplify 4/8 and you get 1/2. That's true. Another way, can't you do the cross multiplication thing? Top left times bottom right. 4 times 2 is 8. 8 times 1 is 8. Yep. Okay. Is that true down in the second one too? Yep. 8 equals 8. Okay. This is called rewriting a proportion by alternation. You'll find that, I think, yeah, you'll see that in your outline. You can also take the crazy thing and flip it upside down. So I'm always going back to the original. If you take this original proportion at the top of the page and rewrite it by this technique, just flip it upside down. Will it be true? Well, let's do it with numbers. Yep, that's true too. This is called rewriting a proportion by inversion. Just flip it literally upside down. Another way to rewrite a proportion that most people don't know about is called rewriting it by addition. Going back to the original, I really should put a rectangle around this. If the boxed one is the original one, what did I do? I took the top plus the, numerator plus the denominator over the denominator equals numerator plus the denominator over the denominator. That's called rewriting a proportion by addition. Now, I haven't demonstrated to you that it works yet. Okay, using the one up here, 4 plus 8 over 8 equals 1 plus 2 over 2. Does it check? Sure, 24 equals 24. Okay, so, and then you can also do it by subtraction, which is very similar. Now you take the numerator minus the denominator over the denominator equals the numerator minus the denominator over the denominator. Or in the case of our problems up here, 4 minus 8 over the denominator equals 1 minus 2 over the denominator. And sure enough, it checks. Negative 8 equals negative 8. Now, you can imagine what's going on here. Let me just start a new page here, and I'm going to make a snapshot too of this one part so we can begin with this. So if we just stay with our same proportion, watch. I'm going to take, so I've taught you what? So far, 4 ways to rewrite. By alternation, by inversion, by addition, by subtraction. But with those 4 methods woven together, you could literally rewrite this proportion into an infinite number of different true proportions. Let me show you what I mean. I could do, for example, let's say the addition. I'm going to use addition, and then inversion, and then alternation. Okay, so if we use addition, that says A plus B is to B as C plus D is to D. That's just a review. Now, take the inversion of that. B is to A plus B as D is to C plus D. And now take the alternation of that. B is to D as A plus B is to C plus D. By the way, what were my original numbers? Wasn't it 4 over 8 equals 1 over 2? Is that right? Okay, let's just do it with numbers to show you that all of these work. Okay, A plus B is to B. That's 12 over 8 equals 3 over 2. Okay, now flip that upside down. 8 is to 12 as 2 is to 3. Now write that by alternation. 8 is to 2 as 12 is to 3. Do you see that the bottom one checks? All of them check. 24 equals 24. Can you imagine I mean, now you could take the inversion of the alternation of the subtraction, and then take the alternation of that, and then take the inversion of that, and you can do this forever. So, why am I showing you this? From one legitimate proportion, how many true proportions can you generate? And the answer is, I can do this infinitely long. I can go on forever and keep creating, as long as I use one of these 4 techniques, I can create any number of things. So it's kind of like, it's from a root, from one proportion we can generate a whole family of proportions. Okay. That's what it means in part 6 when it says any combination of the above any number of times. Now, some things are simple. I mean, some things would be stupid. For example, what would happen if I took the inversion of the inversion? I'm just going to be right back where I started. So that's dumb. I don't mean that. But could I take the addition of the addition? Oh, yeah. So, for example, look at that first one there. 12 is to 8 is 3 is to 2. What's the addition? What if I did the addition of that addition? Wouldn't it be 20 over 8 equals 5 over 2? And you could do that forever, and every one of them is going to be new, isn't it? Yeah. So I'm not saying, wow, you can keep flipping it upside down forever and ever, and holy cow, it keeps coming back to where it was. No. Yes, I know that happens, but that's kind of dumb, and that's not what I'm talking about. Okay. Well, okay, let me go back to my outline, see where we are here. Okay, what I'm going to do is just start covering a few basic, in the remaining minutes today, I'm going to cover some basic terminology regarding trigonometry. And in order to help us with this, I've made a circle that has a radius of 1. You should be able to tell that the radius is 1 by looking at the coordinates of the points. You see how the point on the far right is 1, 0. This point is -1, 0. What does that tell you about this point? 0, 0, 0, 1, and you can't see it, but that's 0, -1. Whoa, that point really got goofed up down there, didn't it? Better get that fixed. It's been abused. There we go. But just to make sure it doesn't get abused again. Get those grouped together. Okay, cool. So, now in this diagram, and by the way, this is because the radius of this circle is 1, we call this a unit circle. And you're going to be hearing a lot of things about this. Probably have already. We're going to look at our angles and our triangles almost every single time in the context of this little grid, this little picture in this unit circle. You'll notice that I have sketched a triangle in here. And that triangle is a right triangle. And you can see then, and this is going to puzzle you a little bit, but when we deal with angles, mathematicians almost always use Greek letters. Just to, I know it may cause confusion, but the whole idea was to avoid it. So whenever you hear a Greek letter, right away you know they're talking about an angle. Anyway, that particular letter is theta, T-H-E-T-A. There's a little bit about the Greek alphabet on your outline if you want to look ahead. Back of the first sheet. You see there's their alpha, beta, delta, pi, theta, sigma. Those are the ones that are used the most frequently. Well, this is a theta that you can see here. And, okay. A habit you're going to see us get into. We always begin along the positive x-axis. This side over here. This is our kind of our 0 mark, okay? This is our beginning. Yeah, that didn't come out very good, so I'm going to erase it. Okay, this is where we begin, at the positive x-axis. And because it's our beginning side, I'll tell you what I will write in here. It's called the initial side. That's better than beginning. Initial side. And do you notice how I rotated to get my angle from that initial side? I rotated in a counterclockwise manner. And that, again, is typical. That's the way we're going to be doing it. When you rotate in a counterclockwise way, that's called a positive angle. And where did we end up? We end up on the terminal side. So the initial side is always the positive x-axis. The terminal side as well, it's wherever we end up. And wherever we end up, you notice that on our grid, the point where our hypotenuse crosses the circle, I've listed the coordinates x comma y up there. You see that? So x, up x, over x and up y. So this point xy is marked for you. Okay? Now, there are such things as negative angles. They would again begin on the initial side, but they would go the opposite direction. And for this, I'm going to use red. So, for example, oh boy, excuse me. What did I do? Why is that so honking? Okay, here's an example of a negative angle. It started at the positive x-axis, but it rotated in a clockwise manner. So this time we went and did this kind of a rotation. That's a negative angle. Okay, positive angles, negative angles. What else do I want to say on here? So, positive angle rotates counterclockwise. Negative angle rotates clockwise. You might think it should have gone the other way, but it doesn't. And now, a very important concept. Here again, I have a picture of a circle, and I've drawn in, R stands for the radius of the circle, and hopefully you can see that there's a radius drawn in horizontally here. There's a radius drawn in horizontally here, and of course those two radii together form an angle. And this is the one that's going to puzzle you a little bit. If this arc along the circle has the length of one radius, Difference is these are straight, but this one is literally curved along the boundary of the circle. If we could make this arc r in length, then that angle formed right there is called 1 radian. And if you look, you can see where it gets its name. It's like radius heaven. Radius, radius, radius. Whoa, we better call that a radian. Now, this is really unique, though, because it's the first time, unless you've had trig before, it's the first time in your life you ever thought of an angle being actually defined by a length. This is really what made that, what made this spread as far as it is? This r, this length. And so it's actually a radius, it's an angle that's defined by this length laid out on the arc of the circle. Okay, now, at the top of the page, are all of you familiar with good old circumference equals 2 pi r? Does that look familiar? The formula for the circumference of a circle is 2 times pi times the radius. And what happens if you divide a circumference by r? You get 2 pi. What does that tell you? It tells me how many of these r's can I get as I go around the circle? How many of them can I get to make a complete circumference? And the answer is, that's how many. So in terms of radians, how many of these can we make to get around the circle? Exactly 2 pi of them. And we proved it up here because if we know this is the length of the whole circumference, and if we simply divide it by this length, we can find out how many of them we can get. So we just found out that 360 degrees can also be named 2 pi radians. And guess what? We're going to, in the next couple weeks, we're going to transform your thinking, because from now on, well, not from now on, but in the next few days, every angle we talk about is going to be in terms of radians. This advantage of a radian being tied to the length is so huge that everything we do from now on is going to be, we're not going to forget degrees, but our main emphasis will be radians. Radians. And so we can start thinking about things like, well, if we start here, this is 0, and we go all the way around, I already know it's 2 pi radians, then halfway around ought to be 1 pi radians, and a fourth of the way around ought to be a half a pi, and 3/4 of the way around ought to be 1.5 pi. And we're going to start dividing the circle, the 360 degrees, into all these different radian names. And I got to take a peek here, but that's kind of, yeah, I've already jumped the gun a little bit, but that's okay. That's where we're going to head next time. So, I guess we'll bring our first trig day to a close. The big points, what makes trigonometry possible, and we've learned what? A lot of things about what you can do with the proportions that come out of similar triangles. Legally, you can rewrite them in all these cool ways. In fact, you could generate legitimate proportions until the day you die, starting right now, and you keep getting new ones, and it would all be true if you followed the rules. And not one would be a duplicate. And then we started talking about this new way of looking at angles. There is no textbook assignment. There will be a couple textbook assignments along the way, but not this time. Study. Yeah, your assignment is study.